Let's take a look at section 7.2. In this section, what we're going to be doing is focusing on tests for associations. So, what that means is that we're going to have two different categorical variables, and we're going to see whether there seems to be one group who maybe has a higher proportion than another group. In this first example, it's actually nothing for us to do on this first example, just kind of to show us like what is the procedure that we go through whenever we're testing to see if there's an association categorically between two different variables. Now, in the first side of this table that we have, again, we have categorically, we have male versus female. The other categorical variable is the type of movie that they might prefer. You've got comedy, horror, drama, and action. Now, we might assume that if you are male, you might like a certain genre maybe more than female, or the other way around. Because someone is female, they might tend to favor one genre more than the other. Now, this right here is just a frequency table, which is showing us just the straightforward count. How many of males said comedy? How many of males said horror? How many of females said da, 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 right? For each of the different options of movies that they had. Now, if there is an association, that's going to mean that there's going to be a proportion of male who like, let's just say, horror more so than female. Or for female, there might be a proportion of one of the types of movies that is a lot higher than that of males. Now, when we do this test for association, let's look at, they call it test for association, or they might say that we're looking for a relationship, which again, for one of the groups, they have a higher proportion in one of the categories for the other variable. When we write the null and the alternative hypothesis, usually we've been using ever since chapter 4, parameter notation, but this is going to be one of the few sections where we actually write it out in words, like sentence form. So the null hypothesis is first going to come along and say, it doesn't matter. It doesn't matter whether you're male or female. You're going to like different types of movies about the same as the other gender. So in other words, gender is not associated with movie preferences, right? Male and female are going to like everything like 50-50, about the same, even split. For the alternative, it's going to say that those two variables are associated, meaning there is going to be some proportion for one of the groups that's higher than the other group for maybe one of the options of movie. Now, in order to make this happen, where again, the usual, we are trying to argue in favor of the alternative that there is going to be a difference for the proportions amongst the groups. We're going to need some null values. And just like any other hypothesis test, there's still going to be the assumption that the null value is true. And then we're going to hope that we find something based on an observed statistic that contradicts it. So if we are going into this with the assumption that the null hypothesis is true, that male and female are going to like all movies, each genre of movie the same, we need to calculate what are known as expected counts. And that's going to be the little formula that we use in order to calculate what would be expected if the null hypothesis is true, that male and female like everything about the same amount. And you can see that it's already done for us. Now, the numbers that you see here, the 51-51, the 25-25, the 26-26, everything's an even split, is not actually what really happened. This is what actually happened, that there was some sort of like variation or differences in the counts for male and female for comedy, wasn't an even split. What this right here is that if it is that the null is true, what would we expect? We would expect a 50-50 split. Now, the way that these numbers get calculated, like we'll do one of them real quick. There is going to be like the use of this formula to make it happen. So the way that they would have gotten this 42 using that little formula is they would take the row total, that's whatever's to the side of that row, and then the column total, whatever's straight below it, and multiply those. So again, all I'm doing right here is just the numerator. The row total times the column total, which is the 84. And then you would multiply those and then immediately divide by the total, which is how many total individuals were in the study, which is 288. And if you multiply those two numbers and divide by 288, you will get 42. And that, again, that's how they got that 42 right here. Now, that would also mean that in order to get all the other 8 numbers, they would have repeated the same little formula, row total times column total, to get each of the expected counts. But what I do like about this example is it shows you very clearly what they mean, that if there is no association, male and female will like comedy the same, like even split, 51-51, horror, 50-50, 25 and 25, 26 and 26, and 42 and 42. That there won't be any difference between the groups for each of the genres of movie. Now, it does seem like this is a little bit tedious to have to like repeat that formula like 8 different times. Usually, as human beings, we're not the ones who do this. We usually give the data to a computer and have it do it for us. But again, we're just looking sort of on the background, like what is the computer doing for us? Now, these values that we just received as representative of the null hypothesis being true, that male and female like everything the same, we want to hope that we have something that contradicts that. So remember the observed, which is up above. We're hoping that we get some contradiction between it and the expected counts. And if we do, it's going to end up with a p-value that'll suggest that the observed was not a fluke, that there is supposed to be some sort of difference between male and female. Now, there is more. There is more to the test for association, which is how do we create a p-value? That's where this formula comes in. Now, each of the calculations that we're about to do or look down here and be doing today are known as contributions. They are what help you create what's known as a chi-squared test statistic. And to try to get this to parallel with things that we've been doing before, remember we would do like Z calculations, and I'm gonna put it in and take it off. And that was the statistic minus the null over the SE. And if that came out to be something that was extreme, we get a small p-value, reject HO, or whenever we did the T test statistic, same little setup there. But each of those were meant to give us a value so that we could get a p-value. And today what they're doing is they're calling it the chi-squared test statistic. And that's its formula there. It's the observed minus the expected. And what we're hoping is that when we compare what was the actual observed values with the expected, that we get some contradiction, that they don't, that there is a distance between them or a difference between them. And the more that there is a difference between them, the more we have a good contradiction to be able to reject the null hypothesis. The only thing that this little formula doesn't do, it shows you that something that you get the differences, you square it, you divide by the expected counts, is that you need to take the sum of the contributions. Now, again, this first couple pages is mainly just to kind of give us insight to like what all is involved as you do a test for association, and the contributions are one of those things. Now, what I'm going to do is I'm going to circle just this one right here as a quick little illustration. Right here, let me get rid of that. Circle this one. Like, how did they come up with that? That's the contribution. What they have right above it is the observed and the expected. So look, here's what I mean. See that little 40? The 40 was right there for the action for male, and the 42 was the action expected for male. And so what the formula says that you do is that you take, starting off first with the observed, and you subtract the expected and you square it. And so that's what the numerator of this is. And again, the more that they differ from each other, the better for having a better chance that the alternative is going to be more likely to be true. Then you would divide by the expected. So you take the 40 minus the 42. And I want you to try this in your calculator before we actually do it with our an actual example that hasn't already been completed for us. And you should see that you get 0.095. And then, yes, that would be something that would need to be repeated for each pairing. For each observed and each expected, you'd subtract, square, divide by the expected, and you would get all 8 of these. It is a tedious process because you have to repeat the formula for each pairing. Then eventually, once you get all 8 of those values, you sum them up. And where this is no different than what we've been doing more recently is if this is on the side of being extreme, again, we'll loosely still use like 2 or more. It's not exactly that when you start doing the like standard normal distribution or the t distribution. You can expect there to be a smaller p-value. This one's looking like maybe not so, but this would be your chi-squared test statistic. And look what they did with it. They took it and they put it there at the bottom to be able to get the p-value using a new distribution that we haven't used yet, but it's known as the chi-squared distribution. It's always just right tail, and you would put down your chi-squared value, and then the p-value, there it is, 0.666, which is not a great, that's the p-value, which is not a great one, because with something like that at 5%, we would not be able to reject the null hypothesis. And again, just referring back to this specific example, there's not enough evidence that there's an association between gender and movie preference. In other words, regardless of whether you're male or female, you might like horror about the same, or you might like romance the same, or comedy the same, or action the same. While maybe some of us might have thought that, yeah, if you're male, you're probably going to like, I don't know, like action more, or if you're female, romance more. No, it seems like there's still maybe evidence that it could be still kind of roughly close to about 50-50 for male and female. At least that's what this sample was suggesting might be true. So now, with that, I want to get us into actually doing an example for ourselves that has nothing has been done yet. What they're doing here is giving us the data for a study where they had women who some experienced a miscarriage and some did not experience a miscarriage. So what they want us to do is to test to see whether having a miscarriage or not having a miscarriage might be associated with the type of painkillers that these women were using. Some of them were using NSAIDs, some acetaminophen, some no painkiller. And you can see right here the frequency, like how often in each of those different types of painkillers, whether they seem to have miscarriages more often or not. Now, again, this is all about proportions. And what we're going to do is just do a test for association. And it's not going to specifically tell us like if one of these options for painkillers tends to have a higher proportion of miscarriages. All it's going to simply do is tell us whether there is an association where one of the types of options does tend to have a higher miscarriage, but it won't specifically tell us which one. That would be something that we would do after the fact. So let's just first off starting to see if what the results even tell us. Now, you'll know that you're doing a test for association because of the verbiage. Here it is. I'm just going to put a box around the word test. It's saying test to see whether the observed data suggests that there's an association. And then here's your variables, the painkiller type, or you can think of it as like the option of painkillers, and then likelihood of miscarriage. In other words, will one of those options for painkiller have a higher proportion of miscarriages than one of the others? So when it comes to writing the null and the alternative, for the null, it's the one that's going to say no, that there's not. That it doesn't matter what you choose to do in terms of painkillers, whether you use them, whether you don't, whatever type you use, you're still going to be as likely as anybody else using any of the other options to have a miscarriage. It doesn't change anything. So we're going to start off with that. That painkiller type and likelihood of a miscarriage are not associated. You can use the word related. And then what someone is arguing for is that they are associated. That maybe if you use one type of drug option or maybe none at all, that you're going to see a higher proportion of that group with more miscarriages. And since we've already specified like the main context in HO, for this one we can keep really short and just counter it by saying the opposite. They are associated as opposed to not. So the not will always go with your HO, and then your HA is going to counter say, no, there is going to be some sort of difference between the groups. Now, keep in mind, these are the values that actually were observed when they collected the data from the women. If the null is true, then what values would we be expecting? And that is where we're going to bring in this first little formula that I've got a little circle around, which says to take the row total times the column total divided by the total. So to get us started, let's do this very first corner box. And so that's going to be take the row total times the column total and multiply them. So in your calculator, you use 75 times 145 and then divide by the total, which is the 1009. Now, when you do that, you should get something like 10 point. Now, what I want to encourage you to do for this particular homework assignment, quiz, test, is that you keep at least one decimal place. Because if you round to 11, it blurs your values a little too much, or you're cutting off too much accuracy. So keep at least one decimal place. And now you start over again. And you don't need to show me any work for this. We're going to move on to the next box. So we're going to do that row total 75 times the 864. And then you'll divide by the total, which is the 1009. And again, keep at least one decimal place. And it should be that you get 64. And then with one decimal place would land us at 2. And then keep going. That's it. It's just repeating the same formula again and again and again. Now let's suppose I was like kind of to skip just for the sake of time. Just go ahead and skip to this one here. Then that would be it's the row total and the column total that you multiply together. Again, I'm not expecting any kind of like work on this, so it's mainly just all calculator. Then divide by the 1009, and that should get you 652. With one decimal would be 0.5. Now that's it. That's how you use the first formula to be able to get each of these values. Again, I'm going to fill in the rest. Again, just repeat. It's the same formula again, again, and again. And then once you have all of these, if you want to do a quick little check, it should be that these add up to give you 75. The second row should add up. The third row should add up. And then also these column, those values should add up to 145. Also contingent, depending on like how you have rounded, it might be a little bit off, but pretty close. Now, what you do with these The hope is these contradict, like for example, the 18 does seem to contradict with the value of the expected. I'll pick another one here, like the what's another good one? Like the 659 and the 652 seem to contradict somewhat with each other. So you're hoping that you do get some contradictions so that you can argue that there is an association, that the two numbers are not, um, you know, there's a discrepancy between them, between the null and what was actually observed. For part C, we're now going to turn to this, which is calculating the contributions. Now, for the contributions, there's going to be in this example six of them, and then we're going to add them together. But note that it's the observed minus expected squared, and then divided by the expected. So let's go ahead and do this one. Now, I'm going to keep it in my screen, and I'm right now working on the 18 and the 10.8. That's the observed and that's the expected, respectively. That's a pairing. So that when we come down here, it's going to be the observed minus the expected squared divided by the expected. And you do need to have that in parentheses, the subtraction, square it, and then divide by that by 10.8, and you should get 4.8. Now I left white space here so that you can, if you need to, it's not required, but you can go ahead and use this as a spot to just set you up with each of the formulas. I don't know, maybe writing it out kind of helps see it before we put in the calculator. And so all I did here was move on to the second pairing, which would be the 57 versus the 64.2. Again, same formula, observed minus expected squared divided by the expected. And down here, all I'm saying is that we can use these blanks as just a spot to keep track of all six of our calculations. And I'll write another one. And again, the order doesn't matter. I'm going to go with the 24 and the 24.7. And this would be now, once you've done a few of these, I hope it starts to feel like, okay, it's very repetitive. And then you just continue to get your values down here. Now I'm going to go ahead and write all six of them. And then again, you don't need to unless you feel like you need a little bit more practice. These should be all six values that we get from repeating the formula for all six of the pairings. So, and then all the pairings would be this. Like you'd have the 148 goes with the 147.3 squared, and then the other one of the other pairings is the 103 minus the 109.5 squared. And then the last pairing, I'm going to show it up there in my screen. It's the 659 versus the 652.5 squared divided by 652.5. Again, the order that you do all six of those calculations doesn't matter because in the end, all you're going to do is like all six of them in whatever order, you're going to add them all up. And that's what I'm about to do right now. Just calculator. Boop, 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 boop. You'll get 6.08. Now, that 6.08 is meant to be a lot like what we've already done, like in chapter 5, chapter 6, with our Z test statistic, our T test statistic. Today it's being called a chi-squared, but it serves the exact same purpose. It's going to be used to get our p-value. And if the p-value is small enough, we'll be able to reject the null hypothesis, which in this particular example is saying that painkillers don't matter. Doesn't matter what you use or if you don't use them, it's not going to change what proportion, right? the proportion of likelihood of having a miscarriage. Now, like what we saw with the T distribution, you need a degree of freedom. And the way we're going to get the degree of freedom, it's actually up here, and it will be this will be provided on the quiz and the test. What you're going to do is you're going to take how many rows and columns you have, but careful, we don't actually count everything. Like I know there's literally like 4 columns there, and there's 5 rows here. What actually counts as a column are just these two from here to there. So there's 2 columns. And then right here, from here to there, there's actually 3 rows that are dedicated to the 3 different options for painkiller. So there's 3 rows. I'm going to do it right here. 3 rows, and you subtract 1. 2 columns, and you subtract 1. And then you multiply those together to get your degree of freedom. So I'm just going to bring those down to the bottom. 3 minus 1, 2 minus 1, right here. 3 minus 1. Oops, sorry. 3 minus 1 times 2 minus 1, which is really just doing 2 times 1, which means we have a degree of freedom of 2. Again, that will be provided. It's something that you'll need to do during your homework. And let's do it. Let's go to the chi-squared test distribution. Now, for this one, you might want to just make a quick little note, because there are other distributions where we have to be really particular about left tail, right tail, two tail. For the chi-squared, it's always just right tail. And so we're going to take all 3 of these important pieces of information and go to the chi-squared distribution, which is a new one for us, but let's go do it. 6.08 with degree of freedom 2. So you can see I'm already here at actually, let me just get out of this. This is I was working on something earlier. Ah, there we go. Stat key. Now the chi-squared distribution, you can see right here theoretical distributions. There's the normal, there's the T distribution, and then there's the chi-squared. You're going to click on that. And immediately it's going to want the degree of freedom. And that's where you'll put the 2. Click OK. And then now we're going to do right tail. And then it's going to default to the p-value of 0.025. That's not our p-value, and it won't be our p-value until we actually, at the bottom right corner, put the 6.08. I'm going to go ahead and click on that right now. Down at the bottom where I have that 7.378. We're going to change it to 6.08 and click OK. And right there, the 0.048 is our p-value. And notice we get a p-value that is just barely significant, 0 point. That's why I was saying it's really important to make sure you keep at least 1 extra decimal. I mean, 2 would have maybe even been better, but 0.048, yeah, 0.048 is our p-value. And if we're doing a 5% level of significance for our alpha, then business as usual. We are able to reject the null hypothesis, which again in this one was saying that there's no association between painkiller or like the option of whatever painkiller you use versus or even if you don't use any painkiller, that there's no relationship with having a miscarriage. But this is saying that there is enough evidence to suggest. Now, I'd say this evidence is probably actually on the weaker side because the p-value being just barely significant at 5%. Now, here's what I was saying at the very beginning of this is that it's telling us what does this mean? It's telling us that if you were to compare for all three of the options of painkiller, the NSAIDs, the acetaminophen, the or no painkillers, that one of those groups would have a higher proportion of miscarriages. The only thing that the conclusion of this is not telling us is which group. Like which of these groups, if they're saying there is some sort of relationship that depending on whether maybe you're in the NSAIDs, maybe you're going to have a higher proportion of miscarriages. It's not specifically telling us like who. So what you would need to do if you were interested in that is to go and take this data set, convert it into proportions, and then compare the rows to see which of the three options had a higher proportion of miscarriages. And again, it's suggesting that that was maybe not a fluke. But that is it. And we're going to do one more, right? Definitely just looking at this, a section that is going to have a bit more number crunching. So you'll want to slow down, make sure that you get all your numbers nice and rounded correctly. But I want to do one more just to really like seal the deal on this procedure. As you can see at the top of this example, it's already given us the formulas, those for the expected, those for the contributions, even for like the degrees of freedom. It's just a different story. And in this one, you might look it up one day. There's a game show, like a British game show called Golden Balls. And the purpose of the game is that two contestants are winning money, and at the end of the show, they have the option whether they want to split it or whether one of them wants to maybe steal it from the other. The only downside is if they both the great thing is if they both decide like, hey, we're gonna split it, great. They're each gonna get like 6,000 and 6,000, right? But if one of them decides to say, hey, I want to split it with you, but the other person deviously says they're gonna that chooses to steal it, then that one person is gonna steal it from the other, or the other way around. But if they're both greedy and both said they're both gonna steal, then they both get nothing, right? So again, interesting game show. Check it out. I mean, of course, like the meanest thing to do is to backstab your partner and steal the money from them. And what this study right here is doing is they're giving us the results from whenever someone is younger versus someone's older. And you might just for yourself, like, what do you think? Do you think that if someone's younger, they're going to be more likely to steal than somebody who's older? I don't know. And that's what we're going to check right now. Is there an association? You know, if you are younger or older, does will you see a difference in the proportion of those who decide to, you know, split it or steal? Right? And usually, whenever I ask my students that are in my in-person class, a lot of them tend to say it's probably the younger people who are going to be more likely to steal and backstab their partner. But let's do this. So there's the word. We're going to do a test to see whether there is an association between the decision to split or steal and somebody's age, whether they're younger or older. So the null is going to come out saying, no, it doesn't matter, right? They're not associated. Split slash steal decisions are not associated to age. Again, the idea behind that is that it doesn't matter if you're younger, older. Everybody's gonna split and steal about the same as everybody else in the other group. And then to counter that, the alternative is going to say, no, they are associated. That one of these two groups is more wicked than the other. Now, for the expected counts, that's where we're going to use this little formula where, again, if we want to get the very first box here, we're going to do the 382 that's its corresponding row to the side, and 303, that's its corresponding total for its column. I'm gonna just put that one over here to the side, 382 times 303 and divide by the big total, 574. Yeah, so 382 times 303, hit enter, and then divide 574, and you should get 201.6. Now, you could, if you wanted to get the next couple boxes, you could just subtract those, the 382 minus the 201.6 to get your next number to fill in the blank. And that's fine if you do. I mean, you'll still at least need the formula to get you started. And then you could use like a series of minuses. Even here, you could do the 303 minus the 201.6 and fill in the gap here. If not, right? If not, then just stick to the little formula. So if I'm doing this one here, it'd be the 192 times the 271, whatever's straight to the side of it, total wise, whatever's straight below it, column wise, multiply those and then divide by the big total, the 574. And you should get 90 for this last one, 0.6. Now, with these, we're going to now do the contributions, which I'll try to get it all into my screen. We're going to start off with the 187, which is way up at the top, and that's going to go with the 201.6. So you just got to make sure you do corresponding observed and expected values. Now, again, if you're thinking like, wow, this kind of seems like a tedious thing. Usually, as like human beings, we don't do this, right? This is just to kind of give us insight as to what the StatKey software is going to be doing for us. But for the test, quizzes, homework, yeah, you'll be asked to go through this process manually, and I won't pick something that's got, more than like I won't give you one of these that has, we have to do this like formula like 20 times or something, 4, 5, 6 maybe. And then we're going to do the 195 minus the 180.4 squared over the 180. And again, you would put each of these into your calculator, and like as you're doing them, just start to collect them down below, which I haven't done yet, but here they come. You'd have like a 1.06, you would have a 1.18, then you would finish your last two. And you're welcome to pause the video and do the last two without me, just to make sure that it's clicking for you in terms of how to use the little squared formula. Actually, maybe go and do that. Yeah, you could pause the video, do the last two of these little pairings for yourself, and then we'll actually start to conclude this one. All right, here it comes. So the last couple ones would be the 116 that's observed minus the 101.4, then dividing by the 101.4, then the 76 minus the 90.6. And so the last two remaining contributions would be 210 and 235. And then as we add those up, that's going to be our chi-square distribution, which is 6.69, which that's pretty good. Remember, we can still, use kind of that tentatively, like anything that's kind of like two-ish or more is extreme. Should get a pretty good size p-value here. That's on the smaller side. Remember, the chi-square distribution is always all we're going to ever need is the right tail. And for the degrees of freedom, it's up there. Rows -1, columns -1. And on this one, we've only got like officially two rows and officially two columns, like younger and older versus split steel. So 2 and 2. So 2 rows -1 times 2 columns -1, which order of operations shows that that's just 1 times 1, which is 1. To go and go back to the chi-square distribution, maybe do it without me, right? If you saw just the same way we did on example 1, click your right tail, make sure that you change the degrees of freedom to 1. In the last example, it was 2. So change it to 1, right tail, put your 6.69 at the bottom right, and you should get a p-value that's pretty good. And I want you even to think about whether with that p-value we should be rejecting HO or not rejecting HO. Maybe even go ahead and write like the conclusion. Yeah, see if you can finish out this problem without me. Just hit the pause, finish it out. All righty. Well, here it comes. You should have gotten 0.0097, which would then lead us to be able to reject the null hypothesis at a significant level of 1%. Yeah, that's smaller than 1%. And anytime you see like 0, something, that's smaller than a decimal that has just 0.0. So we can reject the null hypothesis. There is enough, or you could say strong, because of it being smaller than 1%. I'm just going to go with the classic. There is enough evidence to support, or you can say suggest, that there is an association between split steel decisions and age. So again, it's not telling us who, but it is telling us that yes, if you were to look at the proportions, one of the groups would tend to be on the higher side of splitting than one of the other age group. It just doesn't tell specifically who, but yeah, it'd be worth putting this into the software and looking to see, well, who does have the higher proportion that seems to steal more often. But as far as like showing you real quick, how did we get that p-value, just in case you need it, we would be going back to the chi-squared distribution. I'll start from the very beginning. The chi-squared distribution's here. We would put our degree of freedom, which was just a 1. We would hit the right tail, and down at the bottom, we would type in our 6.69 and click OK. And then there's our p-value that gave us the ability to reject. All right, but that is it. That is another recording down. And so I'll make sure to get this one posted. And again, questions come up, reach out, let me know. Have a good one.